Chapter 1.8.12 Linux Kernel Security Constraints for Pods and Containers. The text explains the security features present in the Linux kernel that can be applied to Kubernetes workloads. It suggests referring to configure a security context for a pod or container to learn how to implement these features. Prior knowledge of Linux and Kubernetes workloads is recommended for understanding and utilizing these security features effectively. Run workloads without root privileges. When deploying a workload in Kubernetes, it is important to use the pod specification to restrict the workload from running as the root user on the node. This can be achieved by using the pod security context to define the specific Linux user and group for the processes in the pod, and explicitly restricting containers from running as root users. It is crucial to set these values in the pod manifest to override similar values in the container image, especially when running images that you do not own. However, it is essential to ensure that the user or group assigned to the workload has the necessary permissions for the application to operate correctly to avoid file access issues or failed operations. Fine-grained control over process actions in the cluster can be achieved by configuring kernel security features, but managing these configurations at scale can be challenging. Running containers as non-root or in user namespaces if root privileges are required can help reduce the need to enforce configured kernel security capabilities. Security features in the Linux kernel. Kubernetes allows users to configure and utilize Linux kernel features to enhance the isolation and security of containerized workloads. The common features include seccomp, AppArmor, and clinux, which help restrict system calls, manage access privileges, and assign security labels, respectively. These features can be enabled in the kernel of the operating system running on the nodes. The security context field in a pod specification is used to define constraints for processes, supporting other security settings such as Linux capabilities and file access permissions. Seccomp allows for the restriction of individual syscalls, helping to sandbox privileges of processes. Container runtimes like CRIO, Docker, and Containerd allow a subset of Linux capabilities by default, which can be further limited using seccomp profiles. It is recommended to use the default seccomp profiles bundled with the container runtime to avoid configuration risks and challenges in profile management. For a more isolated environment, options like gvisor can be considered, although they may require more resources and compatibility issues with certain hardware. AppArmor and SE-Linux are policy-based mandatory access control mechanisms that can be used to strengthen Kubernetes workloads. AppArmor supplements standard Linux permissions by confining programs to limited resources through profiles, while clinux restricts access to files based on labels assigned to processes. Both AppArmor and SE-Linux offer similar protection but differ in configuration methods and policy applications, with AppArmor using profiles and SE-Linux using labels. These security controls can be used together to enhance overall system security, extending protection beyond containers to mitigate vulnerabilities like CVE 29D v736. Managing custom configurations for seccomp, AppArmor, and clinux can be challenging, especially at scale. Tools like the Kubernetes Security Profiles operator can help in managing and distributing these configurations efficiently. Overall, utilizing these security controls in Kubernetes can enhance the security and isolation of containerized workloads. Kernel-level security features and privileged containers. Kubernetes allows for containers to run in privileged mode, granting them access to operating system administrative capabilities. This mode is available for both Windows and Linux containers. Privileged containers override constraints like seccomp, AppArmor, and SC Linux profiles, giving them all Linux capabilities, even those not required. While privileged containers can be useful for tasks requiring administrative permissions, it is generally recommended to avoid using them due to security risks. Instead, specific capabilities should be granted to containers using the security context field. Privileged mode should only be used when necessary, such as when manipulating the network stack or accessing hardware devices. In Kubernetes version 1.26 and later, Windows containers can also run in a similarly privileged mode by setting the appropriate flag in the pod specs security context. It is important to carefully consider the implications of running containers in privileged mode and to follow best practices for security. Recommendations and best practices. Before configuring kernel-level security capabilities, it is recommended to implement network-level isolation. Running Linux workloads as non-root by setting specific user and group IDs in the pod manifest and specifying run as non-root true can enhance security. Additionally, enabling user namespaces by setting host users false in the pod manifest allows running containers as root in the user namespace and as non-root in the host namespace. This feature is still in development and may not have full support yet. Refer to the security checklist and use a user namespace with a pod for more information.